Imagine yourself taking off in an airplane and going into an intense environment that's surrounded by jammer threats. The jammers are blocking your navigation system from accurately tracking your location. Your airplane begins to perform poorly because it cannot gather the navigation information that's needed to complete the mission. Fortunately, there are Serpa navigation systems and advanced GNSS simulators to test these intense, realistic scenarios. Let's briefly talk about the capabilities that Serpas can provide for your navigation system. Controlled Reception Pattern Antennas, or Serpas, can dynamically adapt to jamming and spoofing signal threats. Basically, Serpas find the direction of the interference signal so that they can minimize the jamming signals by null steering and maximize truth signals by beamforming. But before Serpas are integrated and fielded with your navigation system, it is critical to test them in every scenario that they may encounter for verification and validation of their performance. So how are Serpa navigation systems tested? The most cost-effective and flexible solution is the Wavefront Simulation method, because any scenario can be created and repeatably simulated from the comfort of your lab. However, the difficulty with Wavefront Simulation is maintaining phase coherency between the multiple elements of the Serpa. Many Wavefront solutions require you to manually calibrate the time, phase, and power alignment of the system on a consistent weekly or monthly basis, or whenever the system is powered down. This results in many inefficiencies in testing, as the system will be unusable for hours or days at a time until the calibration has been completed. Thanks to the Skydel Simulation Engine, Skydel's Wavefront systems have eliminated the calibration inefficiencies by autonomously time, phase, and power aligning the signals for you. Using real-time monitoring, the signals are assured to be synchronized within 1 degree for the duration of the simulation. This continuous calibration is imperative to keep your signals aligned through temperature fluctuations on the Wavefront system. Now you can focus on the more important tasks of testing, verifying, and validating your navigation performance without calibration concerns. Now let's talk about the signal capabilities. The software-defined architecture of Skydel's Wavefront systems uses GPUs to compute real-time GNSS truth and threat signals. A single simulation can transmit all in-view truth signals of the 4 major constellations. On each truth signal, you can simulate up to 4 multipath signals. In LiveSky, this would equate to around 240 signals for the all-in-view GNSS signals, using just 1 multipath signal. For threat signals, you can simulate over 100 jammers and more than 6 spoofers or repeaters. Like the truth signals, the spoofers and repeaters can simulate the faux signals of the 4 major constellations. A typical spoofer or repeater would transmit about 80 signals, which includes 16 SVs and 5 code types. The total number of signals are quickly adding up to over 400 signals for each element. With the flexibility of our Skydel Wavefront system, we can easily simulate these realistic scenarios. Let's create a simulation. For this example, I will show you a high-powered jamming simulation on a 4-element wavefront, while displaying the real-time phase offset of each element. The scenario will include an aircraft vehicle traveling in a flight path that passes by a CW, AWGN, and BPSK jammer threat broadcasting over the L1 frequency. Each jammer will have a circular trajectory with different starting locations. The flight path will take off at the Long Beach Airport and make a 2.5-minute round trip to land back at the Long Beach Airport. Using the GUI, I can easily set up a circular jammer anywhere on the map. After going to Settings, Interference, and adding a transmitter, I can manually choose the location and the signal to transmit. However, I want the jammers to directly interact with the vehicle as it flies within proximity of the jammer. So, by using Python to communicate with Skydel's API framework, I will easily create this complex simulation. The simulation that I described was quickly set up and ready to go as the pre-simulation calibration has started. Selecting the Wavefront Phase tab at the bottom of the GUI, you will see the calibration steps that takes place. This automatically occurs before the start of each simulation, and for this 4-element wavefront system, it takes about 44 seconds to complete and start simulating the RF to the unit under test. In the graph, you can see the real-time phase offset of each element compared to the reference, element 1. As the flight takes off from the Long Beach airport, it is met with a high-powered CW jammer. You can see the phase offset of each element output about every 5 seconds. The phase offset fluctuates slightly, but continues to stay within 1 degree, even with the close interaction to the high-powered jammer. At the interaction point with the jammer, the receiver would be feeling about 75 dB J to S of jamming. As the flight continues, it is met with other jammers with similar levels of jamming. The continuous calibration of Skydel's wavefront systems gives you the confidence to know that your Serpa navigation system is receiving signals that are properly phase aligned every time you run a simulation.